Bismillahirrahmanirrahim. At first, I want to introduce myself. I'm Ali, a master student in Mullah University. Today, I selected some questions from the last of chapter 3 and 4. I'm talking about these sources, the number one, solid state electronic devices, and number two is the semiconductor physics and devices, basic principles. Now let's come back to our lecture here at this question. Like I said before, these questions, I selected it from the end of chapter 3 and 4. Like we know, at any chapter, at any end of chapter, we have many problems, something like questions, but I don't know the author used this word, problems. Let's start from this problem. This question, we dealing with silicon at room temperature. The silicon is doped with donor impurity atoms at a concentration 6 dot exponential 15 centimeter to force minus 3. Need number one, determine the difference to Fermi energy level from the energy conduction band. Let's solve it. We will start from this general equation. Concentration of electron at the conduction band equal the effective density to conduction band exponential minus the difference between the Fermi level energy level and conduction energy level divided on kT. K, it is the Boltzmann constant, but when T is room temperature, we calculated this result before. It's equal dot 0 to 189. That will be easier to us to can use it. You can prepare the sometimes, okay? Now let's find the result about the difference between Fermi energy level and the conduction band. Let's use the pencil here. Let me use the pencil. Here, we will use something like track, math track. We will put the effective density. We will divide, the concentration of electron divided on effective density of conduction band. After that, we will take ln to the both side, okay, to find here EC minus EF, but here we have minus. How I can delete it? By put the effective density be up and concentration electron be down. By this way, I can delete the minus and without do any change between these brackets, because this bracket will be very important to us, okay? Let me delete all that and complete again, okay? Here, like I said before, the author said is doped with donor impurity atom at a concentration. That's mean here we dealing with n-type doped. In n-type doped, this important option, the concentration of electron directly equal the concentration of donor at the conduction band. That's mean will be divided on the concentration of donor. Like I said before, equals 6 dot exponential 15. Here I prepared, I calculated this equation. The last result, I find the last result was 2 electron volts. But when I searching in another sheet, in another page, I found equal dot 2188 electron volt. I don't know why. Let's depend on this result. Okay, now to solve branch B, say calculate the concentration of addition donor impurity atoms that must be added to move the Fermi energy distance closer to the conduction band. When the author said to us, calculate the concentration of addition donor impurity atoms, that must be, we have ND2, that's mean new concentration of donor at the conduction band, and we have another element, it is ND prime. ND prime, that's mean the difference between conduction donor 2 minus the concentration donors 1. Now let's solve all of these together. Here we know the NC here it's constant because at room temperature, we calculated that before, equal to 0.81 exponential 19. And we know the result about EC minus EF, this EC minus EF1. When I have a new element, I'm talking about ND2, that's mean we have a new bracket, EC minus EF2, okay? Now let's solve that. Like I said, it is the distance of Fermi energy level closer to the conduction band. Here, to find now, like I said before, we know the result about ND1, but we don't know the last result about, we don't know the result about the donor concentration, the new donor concentration on the conduction band. Here, let me use the pencil again. This will be important to us. We can start it from it. Okay. Now, NC is something like constant. We know its result 2.81 dot exponential 18. That's mean we have this. That's mean we have this result. Let me. Let me use this pencil again. How I can do that? That's mean this result. We have this result. That's great. And now KT is something like constant because we know its result, because T is room temperature. Here we just want a problem. We must calculate this new bracket. How we can do that? We can do that by using another. Let me put that here. Okay. We can calculate this new bracket by using this relation between bracket number 2, the difference between the Fermi energy level with the conduction level 2, equal the EC minus EF1 minus KT. After that, we calculated it. The last result was 0.1929 electron volt. We can put this result directly here. We know the result of KT, and see it's constant because we know it because at room temperature. Let me delete all of that. Yes, that's it. Now we know the result about ND2 equal 1.631 exponential 16. the unit actually centimeter to force -3. Now this important here. Like I said before, the additional donor atoms, ND prime, this is my favorite way. I use this prime to can know the difference between these, because actually we're using the same ND. How I can be sure from which one I use it, okay? ND prime, the additional donor atom at the construction band, equal ND2 minus ND1. Now I have all of these results, ND1 and ND2. That's easy. Let me use the pencil again. I have this result, 1.631, and I have this result because the author gave us at the example. That means we can solve directly, find the last result about the additional donor atoms. That's it. Now let me delete all of that. Okay. Now we will dealing with the same needs but with other elements. What that's mean? At first, at branch A, I was dealing with silicon. Silicon has NC, different NC, different NB, and different energy band gap, sure. Now here we will dealing with germanium arsenide, okay? Yes. And the author told us repeat all of that, but by dealing with germanium arsenide at the same room temperature. Here, that means we will start by calculating the difference between energy Fermi level with conduction band. By using the same equation, the same rule, concentration of electron equal effective density to conduction band, exponential minus EC minus EF divided on KT. By using the same trick, let me do that again. Okay. We will divide the concentration of electron divided on effective density conduction band, and the take length to the both side here minus EC minus EF equal KT length concentration of electron divided on EC. How I can delete this minus without do any change inside this bracket? Just I will put NC, the effective density of conduction band, up and the concentration of electron down to find the Fermi energy level for germanium arsenide from the conduction band. Okay, let me delete all of that and keep going. Yes. After that, sure here, because germanium arsenide effective density at room temperature will be different. Here equal 4.7 exponential 17 to the same unit. Here, to calculate that, here we found the equation. After that, KT, we know its result, 0.0259. NC, it's something like constant room temperature. N naught equal ND, the concentration of donors at the conduction band, because we're dealing with p-type dot. If we're dealing with p-type dot, all of these will change. Let's complete. Here EC minus EF equal dot 1593 electron volt. Now the author wanted from us to find the ND prime. And like I said before, ND prime equal ND2 minus ND1. The author actually gives us at first ND1 equal exponential 15 to the same unit, sure. Here, that's mean we don't know the result about ND2, the concentration of donors at the conduction band, but the new one. That means we must calculate us like before. Okay. Let's use this figure. I prefer that. Here we must calculate ND2 to come find the result of ND prime. Now, by here, the author give it this result to us. Now, by using this result, this equation, sorry, ND2 equal the effective density. This will be constant at the twice situation because the same element at the same temperature. This the two important things to us. Exponential minus EC minus EF2 divided on KT. Here we don't have the result of EC minus EF2. Just we have the first result. It was the difference between the Fermi energy level from the conduction band, but the one, not the new one. Okay. How we can find this result? By using this relation. This relation is the new bracket equal the first bracket minus KT. KT will be the same result. Okay, this is important. After that, this result will be dot 13.34.6 electron volts. We will put all of these here. That's mean here now. Now here we have this result. Here something like constant. KT, we know his result. Not anything else. Let me delete all of that and keep going. Okay. By this, now we know the ND2. Put it directly in this equation. Let me use the pencil again. Put it here to find the additional atoms donor to germanium arsenide at room temperature. Thank you about your listening. جرجك درستك قرشروس كان دنيزة باكن. أي والله. Let's stop the recording and go.